Hello, today we're going to look at oxidation reduction. This is the beginning of the Unit 7 material, which is on electrochemistry. Before we get into electrochemistry, we need to go back to chemical reactions and talk a little bit about a different type of reaction, which is known as an oxidation and reduction reaction. Okay, we talked a lot about acid-base reactions and double replacement reactions, and in those reactions, the driving force was the removal of ions. We wanted to remove ions from solution in order for the reaction to happen. While in oxidation-reduction reactions, something different is going to happen. In these reactions, what's going to happen is there's going to be a transfer of electrons from one substance to a new substance, and that is going to be considered our oxidation reduction. One substance is going to undergo what's called oxidation, another one is going to go through reduction. This is very similar to acid-base reactions. If you remember, in an acid-base reaction, the acid is what lost the hydrogen ion, and the base is what took the hydrogen ion. Okay, so it's the same idea, but we're just exchanging protons for electrons for the protons, and we get basically the same kind of idea here. All right, so the idea behind oxidation reduction is to follow the electrons. Since electrons are transferred in these kinds of reactions, we need to be able to figure out where they go. Now, a lot of types of reactions that you've probably talked about in honors chemistry are types of oxidation reduction. So single replacement, combustion reactions, some synthesis, decomposition reactions are examples of places where electrons are transferred. Essentially, if it's not a double replacement reaction, it's not an acid-base reaction, it's not a precipitate reaction, then it will be considered an oxidation reduction reaction. Alright, so very typical, a very common one that most people know offhand is sodium and chlorine coming together to make sodium chloride. Now, when sodium's in its elemental state, it has no electrons. There aren't any electrons that are lost or gained, so it has a charge of 0. Chlorine in the elemental state hasn't lost or gained electrons either, so it's going to have a 0 charge. Now, when these two elements come together, sodium is going to lose an electron to chlorine. So when it makes that transfer of electrons, what you're left with is a sodium plus 1 and a chloride with a minus 1. And that's what we call an ionic compound, the transfer of electrons. The fact that the sodium has a positive charge and the chloride has a negative charge creates this ionic compound. And that's an example of a synthesis reaction where we're synthesizing table salt from sodium and chlorine. And the real reason why it happens is the transfer of electrons, because we know there's no charge here and we end up with a charge over here. Now, combustion reactions are also considered oxidation reduction, and they're a little harder to see. We need to find where the electrons are transferring. Where are the electrons going when they're on the reactant side, and where are they at now on the product side? And it's a little hard to do when we have some complicated decomposition and some combustion and some single replacement reactions. So in order to see this transfer of electrons, we need to have some rules established. And the first rule that we're going to talk about, first thing we're going to talk about is oxidation states. And actually, before I go into that, the whole point of using this right now is that we're going to be looking at creating electrochemical cells, which are really nothing more than batteries. So we're going to be talking about electrons being produced or transferring during a chemical reaction. And that's going to give us battery technology. And that's the reason why we're talking about this right now. Okay, so oxidation states. It's basically a way to keep track of the electrons. Okay, so this is what we use oxidation states for. They're very similar to charges, but they're not really the same thing. Okay, they're not really completely the same thing. If you don't get a difference between the two, you'll be okay in this class, but just keep in mind that oxidation states are not completely the same thing. Now, I gave you a handout back in the first semester with formal charges because I talked about oxidation states, charges, and formal charges, and I show you the difference on that handout. So it might be a good idea to go back and get that handout. Alright, so anyway, two identical atoms are going to share equally. Two different atoms are going, the more electronegative element is going to receive all the electrons. Okay, so when we have shared electrons in covalent compounds, we're going to keep track of the electrons by making this rule happen. If the atoms are sharing electrons, the more electronegative element is always going to get those electrons. Now we know that's not true, but for the sake of oxidation states, we're going to make that true. And if we have an ionic compound, the oxidation state is, of course, whatever the charge is on that monatomic ion. All right, so let's take a look at some rules here for oxidation states. I'm not going to read all of these to you, and you can write this down if you want, but if you download the notes, I have all of this stuff in the notes. This entire video lesson has a note section. If you want to go back into Moodle and download that, you can. All right, so atoms in their standard state, 0. Okay, so anything that's in its elemental state, 0 charge. Monatomic ions, as I just said, they're going to have the same charge. Oxygen is always assigned a -2. okay, in its covalent compound. So if we have oxygen, you're almost always going to be using a -2. The only time that you have this exception is if you have something in peroxides, where you have oxygens bonded to oxygens. The reason for that is that you have oxygen bonded to oxygen, to hydrogen, and to hydrogen. Well, the oxygens here share evenly, so you're gonna ignore that one, and what's gonna happen, it's gonna only get an electron from the hydrogens, so therefore each of those oxygens will be -1. Peroxides always have oxygens bonded to themselves in them. Okay, they don't come up often, and I'll talk about it a little more in class. Hydrogen has a +1 when it's put together with nonmetals, and that's pretty much what you're going to see. It can be -1 when you put hydrogen with metals, because when you put hydrogen with a metal, its electronegativity is a lot higher than the metals, and therefore it will take the electron from the metal. But like I said, more times than not, you're going to see hydrogen bonded with nonmetals, and hydrogen is almost always +1, and oxygen is almost always 2 minus, or -2. Fluorine is always -1. Okay, so these three rules right here are pretty good. Well, actually, all of them. Now I'm thinking about it, but this is what we're doing: is we're setting some basic or some ground state substance. What was the word I'm looking for here? You know, we're trying to find things anchors. These are going to be our anchor elements. That's what I'm looking for. The fact that oxygen is always -2, hydrogen is +1 is going to help us figure out what the other elements are. All right, neutral compounds have a net oxidation state equal to 0. So if it's a compound, we have to make sure that the overall oxidation state for the compound is 0. If it's an ion, okay, then it has to equal the charge of the ion. Okay, I'm going to do some examples and I'll show you what I'm talking about. Okay, so let's take a look at this. Now, here's the terms: oxidation and reduction. Here's what we're talking about. With oxidation is a process that occurs when the oxidation number of the element increases. Elements are going to lose electrons during oxidation. Reduction is a process when the oxidation number is reduced. I like reduction. That makes a lot of sense to me. I can understand that definition. Okay, the oxidation number is going to be reduced in the chemical reaction. Okay, so elements gain electrons in reduction. Now, if you want a couple things to help you remember this, you can do oil rig. If you'd like that, that would help you remember this. You would say oxidation is loss of electrons. R is reduction. Involves gaining electrons. Okay, so oxidation involves loss of electrons. Reduction involves gaining electrons. You could also do Leo says Ger. Okay, this is another way to remember oxidation reduction. L is loss of electrons, oxidation. G is gains, electrons, reduction. Okay, and I have these in the hand. If you go into the notes, I have these spelled out in the notes as well. I like doing this. I like remembering reduction just based on this simple statement right here. This makes more sense to me than those two things up there. So here's what I'm talking about. Let's take a look at this compound here. Okay, we've got carbon and hydrogen. Well, the hydrogen, as I said, when it's bonded to a nonmetal, is always going to be a +1. So what I'm putting up here at the top is I'm putting my oxidation states at the top. And one note about oxidation states, notice that I'm putting the charge in front of the number because this is not a real charge. This is a fake charge. We're just kind of coming up with these charges just to see where electrons are here, and then we're going to compare it to the product side and see if the electrons changed. All right, if we use the same rules for both sides, it should work out. All right, so this is the oxidation state for hydrogen. Hydrogen is a +1 in methane. Now, there's four hydrogens, so therefore all the hydrogens sum up to a +4. Now my carbon compound, or the methane, has to have a 0 charge. So what does my carbon have to be? My carbon has to be a -4. So therefore, what's the oxidation state on a single carbon? A single carbon carries a -4 charge. Now, we know carbon isn't -4. It doesn't have a charge. It's not ionic. But the idea is that we're just using those rules that I established earlier to set these, saying that the more electronegative element is holding on to the electrons. Now, oxygen's in its elemental state, so there's no transfer of electrons. It's oxygen bonded to oxygen, so therefore 0. Electronegativities are the same. We have a 0 here. Now, on the product side, oxygen's now in a compound, and we always said if it's not a peroxide, oxygen is going to be a -2. It's a very high electronegativity, and it was almost always going to do this. So if I have a -2 for the oxygen, and I have two oxygens, I have a total of -4. Now, if carbon switches from being bonded to hydrogen to now being bonded to oxygen, it's changing its oxidation state. It's going from a -4, you have to balance the charges so that the overall compound comes out to 0, and the individual charge on carbon is now a +4. Notice what happened. Carbon went from -4 to +4. Its oxidation state has changed. Oxygen went from a 0 charge to now being -2. So what's happening is oxygen is reacting with this, and it's taking electrons from these elements and creating this compound. And as a result of taking electrons, it then becomes bonded to the carbon as a result of that. Now oxygen will become -2, so therefore its charge is being reduced. So that is my reduction. I can right away tell that oxygen is undergoing reduction. I like looking at the reduction because I'm looking for the reduction of the oxidation state or the oxidation number. Okay, that's the same as saying state. All right, so then carbon has to be undergoing oxidation because its charge is going up. What's happening in this process is that carbon is going from a -4 to a +4. So it is undergoing oxidation. So this would be oxidation, and we would have reduction. And it's going to be important because we're going to split these reactions into pieces in the next topic, or the next video where I show you how you balance. Okay, now over here, oxygen is -2, hydrogen is +1. -2 for the oxygen, and I have two hydrogens which have to balance out to +2, so therefore each hydrogen has to carry a +1 charge. And that pretty much matches what we said earlier. So that's how you determine oxidation states. You can compare them based on the reactants and products, and you compare them and see, well, what happened? How did electrons transfer from reactants to products? What was going on? All right, one last thing to leave you with is this big fancy word called disproportionation. Sometimes what happens is you can have a single substance that undergoes both oxidation and reduction. Don't worry about these terms about oxidizing agent and reducing agent. AP is dropping those out. The idea is that one single substance is both oxidized, okay, undergoes oxidation and reduction, okay, and reduced. So one single substance goes through this. So let me show you the first example, and you can kind of figure out the second one if you want. -1 for oxygen in a peroxide, because we're in peroxides now, so this is hydrogen peroxide, you have O2 here, and this is most likely the only peroxide you're really going to ever see, guys, so don't freak out too much. So -2, because I have two oxygens, so +2 for my hydrogen, so of course hydrogen has to be +1. And that should clue you in that this is going to undergo a different charge note, because you put a -2 here, you're going to get a strange charge for hydrogen. Hydrogen is not going to be anything but +1 or -1. Never going to be anything like that. It's only -1 when it's bonded to a metal. Oxygen in water is a -2, +1 for the hydrogen, and a 0 for the oxygen. So take a look at what's going on here. I'm going to do blue for the reduction. So what's going through reduction? Well, the oxygen is going from a -1 to a -2. So that would be reduction. Oxygen is undergoing reduction. Now I'll do green, I'll do the oxidation. What's going through oxidation? Again, oxygen is going through -1, and it's going up in charge to 0. So it's going through both oxidation and reduction because it's both true. Notice the hydrogen doesn't do anything. It just moves as the oxygen makes this change. That's referred to as disproportionation. One substance, the hydrogen peroxide, undergoes both oxidation and reduction. All right, so take a look at that for a little bit, and then watch the video on how to balance oxidation reduction reactions, and I will see you guys soon.